September 9, 1940. 11:47 in the morning. A 35-year-old British scientist named Frederick William Meredith sat alone in his cramped office at the Royal Aircraft Establishment in Farnborough, England. Outside, German bombers were tearing London apart. The Blitz had begun just 2 days earlier. And here was Meredith, a man with no military rank, no combat experience, just a pencil, a slide rule, and an obsession that his colleagues called insane. He had calculated something that defied every principle of aircraft design. Something so counterintuitive that senior engineers laughed when he presented it. Heat, the eternal enemy of aviation, could become thrust. Waste energy could push an airplane forward. The laws of physics said it was possible. Everyone else said he was mad. 5 years later, his impossible theory would be buried inside the belly of a silver fighter plane. That plane would escort American bombers all the way to Berlin and back. It would shoot down more enemy aircraft than any other American fighter. It would help win the war in Europe. The numbers tell the story. The P-51 Mustang achieved 437 miles per hour, faster than any production fighter of its era. Its secret was not a bigger engine, not a sleeker wing. It was a radiator scoop that turned physics upside down and reduced cooling drag to zero. But how did a rejected theory from a forgotten scientist end up saving thousands of lives? And why did it take 5 years for anyone to believe him? This is the story they never told you about World War II. Let me take you back to where it all began. The year is 1935. Aviation is exploding, literally and figuratively. Aircraft speeds have finally broken 300 miles per hour, and engineers around the world are celebrating. But behind closed doors, they are terrified, because faster speeds have created a problem that nobody knows how to solve. The problem was heat. Massive engine-killing heat. You see, aircraft engines in the 1930s came in two flavors. Air-cooled radials looked like angry metal flowers bolted to the front of the plane. They worked fine at low speeds, but they created enormous drag. Their flat circular shape punched through the air like a dinner plate. At 300 miles per hour, that drag became a serious limitation. Liquid-cooled engines were sleeker. They could be wrapped in smooth aerodynamic cowlings that sliced through the air like a knife. The Rolls-Royce Merlin, the Daimler-Benz DB601. These magnificent power plants promised higher speeds and better high-altitude performance. But liquid-cooled engines had a fatal weakness. They needed radiators. Think about your car for a moment. That radiator sitting behind your grille. It works because air flows through it while you drive. The air absorbs heat from the coolant and carries it away. Simple. Effective. But your car is traveling at 60 miles per hour, not 300. At aircraft speeds, radiators became nightmares. A typical 1930s aircraft radiator was essentially a brick of aluminum fins sitting directly in the airstream. It created so much drag that it could slow an airplane by 40 or 50 miles per hour. Engineers tried hiding radiators inside the fuselage under the wings, even retracting them during high-speed flight. Nothing worked well enough. The numbers were brutal. The German Messerschmitt Bf 109G lost 14% of its total thrust just to cooling drag. 14%. Opening the radiator flaps at high power could rob 30 miles per hour from its top speed. The British Spitfire was slightly better, but still suffered 8 to 10% losses. In 1935, this was considered an unsolvable problem. Liquid-cooled engines needed radiators. Radiators created drag. Drag reduced speed. Speed won dogfights. Therefore, every liquid-cooled fighter was permanently handicapped. Every engineer in Europe had accepted this as fact. Every engineer except Frederick William Meredith. Meredith was not famous. He was not wealthy. He was not even particularly well connected. He was simply a physicist who asked questions that others considered stupid. One afternoon in early 1935, Meredith was reviewing data on radiator installations. The same depressing numbers everyone else had seen. Drag coefficients, pressure losses, heat rejection rates. But Meredith noticed something that others had overlooked. The air leaving the radiator was hot. Obviously, everyone knew this. That was the entire point of a radiator. Cold air goes in, hot air comes out. But Meredith started calculating what that heat actually meant in terms of energy. A Rolls-Royce Merlin engine running at full power wastes approximately 400 horsepower in heat. 400 horsepower. That thermal energy has to go somewhere. In a conventional radiator, it simply heats the exhaust air, which then tumbles away in a turbulent wake, creating even more drag. But what if you could capture that energy? Meredith pulled out his thermodynamics textbooks. He started scribbling equations. Hot air expands. Expanding air in a confined space accelerates. Accelerating air creates thrust. It was basic physics. The same principle that makes a hot air balloon rise. The same principle that powers a jet engine. Heat equals energy. Energy can be converted to motion. By July 1935, Meredith had worked out the mathematics completely. If you built a radiator duct with exactly the right geometry, you could create what he called a thermodynamic recuperator. Cold air would enter a carefully shaped inlet. It would slow down and compress slightly, like water backing up behind a dam. Then it would pass through the radiator, absorbing massive amounts of heat. The heated air would expand and accelerate through a converging exit nozzle. The exhaust velocity could actually exceed the aircraft's forward speed. When exhaust velocity exceeds forward speed, you have net thrust. The radiator would not just stop creating drag, it would push the airplane forward. Meredith called this the Meredith Effect. His colleagues called it ridiculous. On August 14, 1935, Meredith published his paper. The title was impossibly dry. Cooling of aircraft engines with special reference to ethylene glycol radiators and closed-in duct. 23 pages of equations, diagrams, and careful analysis. Nobody cared. Oh, a few engineers read it. Some tried to implement his ideas. The supermarine team building the Spitfire incorporated a ducted radiator based loosely on Meredith's concepts. But they got the geometry wrong. Their duct was too short. The inlet angles were too steep. Airflow separated from the walls and became turbulent, destroying any chance of thrust generation. The Hawker Hurricane tried something similar. Same problems, same disappointment. The Germans never even attempted it. Their Bf-109 used conventional wing-mounted radiators that bled speed like open wounds. By 1940, Meredith's theory was considered an interesting failure. Theoretically possible, practically impossible. The physics worked on paper, but nobody could build hardware that matched the equations. Meredith himself had given up trying to convince anyone. He continued his research on other topics, quietly watching as British fighters struggled against the Luftwaffe with their drag-burdened cooling systems. Then, 6,000 miles away in Los Angeles, California, a man named Edgar Schmood received a very unusual phone call. Schmood was 41 years old, Austrian-born, and obsessed with aerodynamic efficiency. He had worked at Fokker in the Netherlands and General Aviation in the United States before joining North American Aviation as chief designer. He had a reputation for perfectionism that bordered on the pathological. In April 1940, the British Purchasing Commission contacted North American Aviation with an urgent request. Britain was losing pilots faster than it could train them. They needed fighters, and they needed them now. The British wanted NAA to build Curtiss P-40 Warhawks under license. It was a decent fighter, nothing special, but the production lines existed. NABA President James Dutch Kindleberger saw an opportunity. What if they could design something better than the P-40? Something faster, longer-ranged, more efficient. The British were skeptical. How long would that take? Kindleberger made a promise that shocked everyone in the room. 120 days. 4 months from contract signature to flying prototype. The British laughed. Then they agreed. What did they have to lose? Edgar Schmood did not laugh. He immediately started assembling his team and began studying every piece of data he could find on European fighter design. He obtained wind tunnel results from the Curtiss XP-46 program. He reviewed reports on the Spitfire and Hurricane. He read technical papers from Britain, Germany, and France. And somewhere in that mountain of documents, he found Frederick William Meredith's 1935 paper. Schmood read it 3 times. Then he started calculating. The theory was sound. The mathematics were impeccable. The only problem was execution. Every previous attempt had failed because engineers treated the radiator duct as an afterthought. They made it short because long ducts were heavy. They made the angles steep because shallow angles required more space. They ignored boundary layer effects because nobody really understood them. Schmood understood them. And he was about to build something that nobody thought was possible. The P-51 Mustang's radiator scoop would be unlike anything that had ever flown. It would vindicate a forgotten scientist. It would terrify German pilots. And it would change aviation history forever. But Schmood had exactly 102 days to make it work. The clock was already ticking. In Part 2, we will follow Schmood into the drafting room where his team made decisions that seemed crazy at the time. A radiator mounted behind the cockpit. An inlet that looked like a shark's mouth. An exit duct shaped like a rocket nozzle. Each choice was a gamble. Each gamble had to pay off perfectly. The first test flight was scheduled for October. If the cooling system failed, the engine would overheat and seize. If the drag was too high, the aircraft would be too slow to survive combat. If the boundary layer calculations were wrong, the entire project would collapse. Edgar Schmood was betting everything on a 5-year-old paper written by a man he had never met. Would the Meredith Effect finally work, or would physics betray them both? 102 days. That was all Edgar Schmood had promised the British. 102 days to design, build and fly a fighter aircraft that would outperform everything in the sky. A fighter with a cooling system based on a theory that every engineer in Europe had already declared impossible. In Part 1, we watched Frederick William Meredith discover the physics that could turn waste heat into thrust. We saw his paper ignored for 5 years while German bombers burned London. We followed Edgar Schmood as he stumbled upon that forgotten research and made a decision that would either revolutionize aviation or destroy his career. Now the real work begins. The date is April 10, 1940. Schmood has assembled his design team in a cramped drafting room at North American Aviation's Inglewood facility. 12 engineers, 40 rolls of drafting paper, and a deadline that everyone in the room knows is impossible. But the British are not the only ones watching. Across the Atlantic, the Luftwaffe is winning. France will fall in 6 weeks. Britain will stand alone. Every day that passes means more pilots dead, more cities burning, more ground lost. And here is where everything almost fell apart. 3 weeks into the project, Schmood presented his radiator concept to NOAA's senior management. The room went silent. Then the question started. You want to put the radiator where? Behind the cockpit. Underneath the fuselage. In a scoop that would extend nearly 3 feet below the aircraft's belly. That's 30 inches of additional frontal area. You're going to create more drag, not less. Schmood shook his head. The scoop will create almost zero drag. Maybe even negative drag. Howard Kindleberger, the company president's brother and head of engineering, leaned forward. Edgar, I've seen the Spitfire data. I've seen the Hurricane numbers. Ducted radiators don't work. Not the way Meredith claimed. The British got the geometry wrong, Schmood replied. Their ducts are too short, their inlet angles are too steep. They're creating turbulence before the air even reaches the radiator. And you think you can do better? I know I can do better. The room erupted. Vice President Lee Atwood argued that the unconventional design would spook the British Purchasing Commission. Chief Test Pilot Vance Breese warned that an untested cooling system could destroy the prototype. Financial Director Harold Heimbinger calculated that design changes this late would blow the budget by 15%. Schmood stood alone against all of them. Gentlemen, he said quietly, we have 2 choices. We can build another P-40 with a different name and hope the British don't notice. Or we can build the fastest fighter in the world and give them something worth dying for." The room went silent again. Dutch Kindleberger, who had been listening from the doorway, finally spoke. "How long is this radiator duct of yours?" 29 inches from inlet to radiator face. 3 times longer than the Spitfire. "And you're certain about the mathematics?" Schmood pulled out his calculations. Page after page of equations based on Meredith's original paper, extended and refined for the specific conditions of high-speed flight. The diffuser angle never exceeds 7 degrees. Boundary layer separation is eliminated by a scupper inlet. Exit geometry is a true convergent nozzle. The theory is sound. We just need to execute it properly. Kindleberger studied the numbers for a long moment. Then he made a decision that would change aviation history. Build it. But if this scoop creates more than 5% additional drag in wind tunnel testing, we're going back to conventional radiators. You have 3 weeks to prove your concept. 3 weeks. 21 days to validate 5 years of ignored theory. Schmood barely slept. His team worked in shifts, drafting detailed drawings of the radiator installation, while simultaneously building a full-scale mock-up for wind tunnel testing. The scoop geometry was critical. Every angle, every curve, every surface had to be perfect. The inlet design alone went through 14 iterations. Too wide, and it would capture turbulent boundary layer air. Too narrow, and it would starve the radiator of cooling flow. Schmood settled on a rectangular opening with a carefully shaped lip that would skim only the clean, high-energy air from above the aircraft's skin. Behind the inlet, the duct expanded gradually. This was the diffuser section, where fast-moving air would slow down and compress. Meredith's equations demanded a maximum expansion angle of 7 degrees to prevent flow separation. Schmood designed for 6.5 degrees building in a safety margin. The radiator matrix itself was a dense block of aluminum fins surrounding copper tubes filled with ethylene glycol coolant. Hot coolant from the engine entered at 212 degrees Fahrenheit. The cooling air absorbed that heat and expanded dramatically. Behind the radiator, the magic happened. The duct narrowed into a convergent nozzle with adjustable exit doors. Close the doors during cruise, and the heated air would accelerate through the restriction. Open them during climb and ground operations for maximum cooling at the expense of drag. On May 15, 1940, the full-scale mock-up entered Enobayé's wind tunnel. Schmood watched through the observation window as technicians increased airspeed to simulate 350 miles per hour. Pressure sensors embedded in the duct walls fed data to recording instruments. Temperature probes measured heat transfer rates. Smoke generators revealed airflow patterns. The first numbers appeared on the recording drums. Pressure recovery at the radiator face, 84%. Schmood blinked. 84% was exceptional. The Spitfire achieved barely 65% with its short, steep duct. Higher pressure recovery meant less energy wasted, more efficient heat transfer, and smoother airflow throughout the system. But the critical measurement was exit velocity. The technicians adjusted the nozzle doors to various positions, recording data at each setting. With doors fully closed, simulating high-speed cruise, the exit velocity reading came through. 372 miles per hour. The tunnel was running at 350 miles per hour equivalent airspeed. Exit velocity exceeded inlet velocity by 6%. The Meredith effect was real. The radiator system was producing measurable thrust. Schmood's hands were shaking as he reviewed the data. 5 years after Meredith published his paper, someone had finally built a working implementation. The scoop didn't just reduce cooling drag. Under the right conditions, it actually pushed the aircraft forward. The word spread through NADA's facility like wildfire. Engineers who had dismissed Schmood's design as theoretical nonsense crowded into the wind tunnel control room to see the results. The numbers didn't lie. Cooling drag at high speed was effectively 0. But wind tunnels are not real airplanes. Dutch Kindleberger approved continued development, but he issued a warning. Wind tunnel data is one thing. Flight test data is everything. If this system doesn't perform in the air exactly as it does in the tunnel, we're back to square one. The prototype NA-73X took shape through June and July of 1940. Sheet metal workers formed the distinctive belly scoop from aluminum alloy. Welders joined the complex duct sections. Assembly technicians installed the three separate heat exchangers, engine coolant, radiator oil cooler, and intercooler. Everything had to fit within the carefully calculated geometry. Too much internal restriction would destroy pressure recovery. Too little, and the air wouldn't reach sufficient temperature for effective acceleration. On September 9, 1940, exactly 102 days after contract signing, the NA-73X rolled out of Eneboe's factory. Silver paint gleamed under California sunshine. The distinctive belly scoop looked almost organic, like the gill of some great metallic fish. Test pilot Vance Breese climbed into the cockpit for engine runs. The Allison V-1710 coughed, caught, and roared to life. Coolant temperature stabilized at 210 degrees. Oil temperature held steady. The cooling system worked on the ground. But ground operations tell you nothing about high-speed performance. First flight was scheduled for October 26, 1940. Breese would take the prototype to 10,000 feet and evaluate handling characteristics. Then he would open the throttle and see if Schmood's radiator actually worked. The morning of the 26th dawned clear and cool. Perfect flying weather. NAA personnel lined the runway at Mines Field, the company's test facility. British Air Commission representatives watched from a covered observation area. Dutch Kindleberger stood beside Schmood, neither man speaking. At 10:14 a.m., Breese released the brakes and accelerated down the runway. The NA-73X lifted off smoothly, climbing into the California sky. Ground observers watched the silver shape grow smaller, then disappear entirely. 15 minutes passed. 20. 25. Then Breese's voice crackled over the radio. "Inglewood, this is Breese. I'm indicating 382 miles per hour at 15,000 feet. Coolant temperature is stable at 208. Oil temperature normal. No signs of airframe buffeting." 382 miles per hour. The P-40 Warhawk NABA's proposed license-build aircraft maxed out at 360. The NA-73X was already 22 miles per hour faster with an inferior engine. But the real test was coming. "I'm going to close the radiator doors and push to maximum speed." Schmood held his breath. Breese advanced the throttle. The Allison screamed at maximum continuous power. Airspeed climbed. 390, 395, 400. The radiator exit doors were nearly closed. According to the wind tunnel data, exit velocity should now exceed forward speed. The scoop should be producing thrust. "Inglewood, I'm showing 403 indicated. No temperature rise. Repeat, no temperature rise. The cooling system is handling full power with doors almost completely closed." It worked. The impossible theory actually worked. When Breese landed 40 minutes later, he taxied directly to where Schmood stood waiting. The test pilot climbed out of the cockpit with a grin that stretched from ear to ear. "Edgar, I've flown a lot of airplanes. I've never flown anything that felt this clean. Whatever you did with that radiator, it's like the cooling system isn't even there." The British representatives were already on the telephone to London. North American Aviation had just built the fastest fighter aircraft in the Western Hemisphere, and they had done it in 102 days with an engine that wasn't even particularly powerful. When the more capable Rolls-Royce Merlin replaced the Allison in 1942, the P-51B achieved 437 miles per hour. 15 to 20 miles per hour of that advantage came directly from Schmood's radiator design. In air combat, that margin meant life or death. But success brought new challenges. The Germans weren't stupid. When P-51 started appearing over Europe in December 1943, Luftwaffe intelligence immediately noticed the unusual belly scoop. Captured aircraft were examined in detail. German engineers realized what Schmood had accomplished. They tried to copy it. The Focke-Wulf Ta-152 incorporated a similar ducted radiator installation. But the war was already turning. Germany lacked the manufacturing precision and quality control to replicate NODA's exact geometry. Their copies never achieved the same efficiency. Meanwhile, Frederick William Meredith watched from England as his impossible theory proved itself in combat over Berlin, Dresden, and Munich. He never received public credit. He never became famous. He simply continued his research knowing that somewhere in the sky, his mathematics were saving lives. The P-51 Mustang would go on to become the most successful American fighter of World War II. Over 15,000 were built. They shot down 4,950 enemy aircraft. They escorted bombers on missions that broke the back of the Luftwaffe. And buried in every single one of them was a radiator scoop that turned 5 years of ignored physics into battlefield victory. But there was one more secret hidden inside that belly scoop, a secret that would take another 80 years to fully understand. Modern engineers using computational fluid dynamics and precision testing equipment have discovered something that even Schmood didn't realize. Racing P-51s modified with thinner, more efficient radiators achieve exit velocities 8% higher than forward speed. They don't just eliminate drag, they actually produce measurable forward thrust. Frederick William Meredith was right all along. Heat could become thrust. Waste could become weapon. The impossible was merely difficult. In Part 3, we will explore how the P-51's success changed the entire trajectory of strategic bombing over Europe. How German fighter defenses collapsed once Mustangs could escort bombers all the way to Berlin. And how one overlooked detail in the cooling system design almost caused a catastrophic failure that would have killed thousands. The Meredith Effect had proven itself. But the war was far from over. And the biggest challenges were still to come. In Part 1, we watched Frederick William Meredith discover the physics that could turn waste heat into thrust. His 1935 paper was ignored for 5 years while the world burned. In Part 2, Edgar Schmood built the impossible. 102 days. One revolutionary radiator. One aircraft that defied everything engineers believed about cooling systems. The NA-73X flew at 403 miles per hour with a cooling system that created zero drag. Now the P-51 Mustang was heading to war. But success in California meant nothing if the aircraft couldn't survive over Europe. The Luftwaffe had been shooting down Allied bombers for 3 years. German pilots were experienced, ruthless, and flying some of the finest fighters ever built. The Bf-109 and FW-190 had already destroyed thousands of American and British aircraft. When the first P-51s arrived in England in late 1943, German intelligence officers studied reconnaissance photographs with growing concern. That strange belly scoop, that sleek profile. Something was different about this American fighter. They had no idea how different, and they were about to find out in the most brutal way possible. December 1943. The 8th Air Force was bleeding to death over Germany. American strategic bombing doctrine promised that heavily armed B-17 flying fortresses could defend themselves against fighter attack. The theory sounded reasonable. Pack enough machine guns into a tight formation and fighters won't dare approach. The theory was wrong. German pilots developed tactics that exploited every weakness in bomber formations. Head-on attacks minimized exposure time. Rocket-armed fighters could fire from beyond machine gun range. Concentrated assaults overwhelmed defensive fire. The numbers were catastrophic. On August 17, 1943, the 8th Air Force sent 376 bombers against ball-bearing factories in Schweinfurt and aircraft plants in Regensburg. 60 bombers were shot down. Another 176 were damaged. Over 600 American airmen killed or captured in a single day. October 14th brought Black Thursday. Another Schweinfurt raid. Another disaster. 77 bombers destroyed, nearly 200 damaged, 100 bound on Mars. The 8th Air Force lost more aircraft in 1 week than it could replace in a month. American generals faced an impossible choice: continue deep penetration raids and lose the entire bomber force, or abandon strategic bombing and let German industry operate unmolested. They needed fighters that could escort bombers all the way to Berlin and back. The P-47 Thunderbolt had the firepower but not the range. The P-38 Lightning had the range but lacked high-altitude performance. Neither could stay with the bombers throughout the entire mission. The P-51 Mustang could do both. Its Meredith Effect radiator system meant lower drag, which meant longer range on the same fuel load. Its laminar flow wing meant higher speed at altitude. Its Packard Merlin engine meant power where it mattered most. On December 13, 1943, the 354th Fighter Group flew its first escort mission over Europe. 43 P-51Bs accompanied bombers attacking targets in Germany. Luftwaffe controllers detected the incoming raid and scrambled interceptors. German pilots climbed to attack altitude, expecting the usual scenario. American fighters would turn back at the limit of their range. Bombers would be defenseless. The slaughter would begin. The American fighters didn't turn back. For the first time in the air, war over Europe, escort fighters stayed with the bombers past the German border, past the Ruhr, past targets that had always been beyond reach. German pilots were confused. These small, sleek aircraft looked different from P-47s. They flew differently, faster, more maneuverable at altitude, and they kept coming. Intelligence reports flooded Luftwaffe headquarters. New American fighter type. Single engine. Liquid-cooled. Unusual radiator installation. Performance exceeds Bf-109G at all altitudes above 20,000 feet. Reich Marshal Hermann Göring reportedly exploded when he learned that American fighters had appeared over Berlin. "When I saw Mustangs over Berlin, I knew the jig was up." But even as P-51s proved themselves in combat, a crisis was developing back home. Production of the Mustang was accelerating rapidly. North American Aviation's Inglewood plant was building aircraft around the clock. A second factory opened in Dallas. Britain's Packard Motor Company was manufacturing Merlin engines under license. In January 1944, a troubling pattern emerged from maintenance reports: radiator leaks, coolant loss, engine overheating. The beautiful Meredith Effect scoop that had performed perfectly in testing was failing in operational conditions. Not often, not predictably, but enough to ground aircraft and kill pilots. The problem was vibration. Combat maneuvering stressed the airframe in ways that test flights never replicated. High G turns, violent evasive action, diving attacks followed by maximum power climbs. The radiator mounting brackets couldn't handle the accumulated fatigue. Schmood's team investigated frantically. Every grounded P-51 was examined. Every failure point was analyzed. The solution required redesigned brackets with additional reinforcement. Simple in concept, but complex in execution. Meanwhile, criticism mounted. Some Army Air Force officers argued that the belly scoop design was fundamentally flawed. They wanted to abandon the Meredith Effect entirely and switch to conventional wing-mounted radiators like the British Spitfire. Schmood fought back. The radiator system saves 15 miles per hour at cruise speed. That translates to 50 extra miles of combat radius. You want to give that up because of a bracket problem we can fix in 30 days. The debate reached Washington. General Henry Arnold, commander of the Army Air Forces, made the final decision. Continue production. Fix the brackets. The performance advantage was too valuable to abandon. By March 1944, the reinforced radiator installations were flowing into both factories. The leak problem disappeared, and the P-51 was about to prove its worth in the most important air battle of the European War. March 6, 1944. Big Week had just ended. 7 days of maximum effort bombing against German aircraft factories. The Luftwaffe was reeling, but not broken. Today's target was Berlin itself. The 8th Air Force assembled the largest bomber formation ever sent against the German capital. 730 B-17s and B-24s carrying nearly 2,000 tons of bombs. Their mission was simple: destroy the heart of the Reich. The Luftwaffe assembled everything they had left to stop them. Over 400 German fighters scrambled from airfields across northern Germany. Bf-109s, Fw-190s. Twin-engine, Me-410 destroyers armed with rockets. This would be the decisive engagement. Win here, and American daylight bombing might be crippled permanently. Escorting the bombers were 801 American fighters. P-47 Thunderbolts would cover the penetration to the German border. P-38 Lightnings would provide mid-range support, and 187 P-51 Mustangs would go all the way to Berlin. The formation crossed the Dutch coast at 11:42 hours. German radar tracked them immediately. Fighter controllers began vectoring interceptors toward the bomber stream. First contact came over Brunswick at 12:15. A gruppa of Bf-109s dove through the high escort heading for the lead bomber box. P-47s engaged immediately. The sky erupted in contrails and tracer fire. The bombers pressed on. More German fighters appeared. Me-410s climbing from below. Fw-190s attacking from the flanks. The defensive gunners opened fire. Black puffs of flak began exploding among the formation. And then, the P-51s arrived. Captain Don Gentile of the 4th Fighter Group was leading a flight of 4 Mustangs at 28,000 feet when he spotted the attack developing below. German fighters were forming up for a concentrated assault on the lead bomber wing. If they succeeded, the formation would break apart. Scattered bombers were easy prey. Gentile pushed his throttle forward. The Merlin screamed. His airspeed indicator climbed past 400 miles per hour. The Germans never saw them coming. Gentile's flight dove through a formation of 12 Bf-109s like wolves through sheep. First pass. 2 Germans spinning down in flames. Second pass. Another pilot bailing out. The remaining Germans scattered, their attack broken before it began. Across the sky, similar engagements were erupting. P-51s used their speed advantage to intercept German formations before they could reach the bombers. Dive, attack, climb, repeat. The Mustang's near-zero cooling drag meant it could sustain high-speed maneuvering longer than any German fighter. Over Berlin itself, the air battle reached its climax. Major James Howard of the 354th Fighter Group found himself alone against 30 German fighters attacking a bomber formation. His wingmen had been separated in the chaos. Standard doctrine said to disengage and rejoin friendly forces. Howard attacked anyway. For 30 minutes, Howard single-handedly defended his bombers. He shot down at least 4 German aircraft. He damaged several more. He drove off attack after attack, his P-51 dancing through a sky filled with tracers and explosions. When he finally landed in England, his aircraft had been hit by numerous bullets. His guns were empty. He had been fighting on nothing but skill and the aerodynamic advantages that Edgar Schmood had designed into his aircraft. Howard received the Medal of Honor, the only fighter pilot in the European theater to earn that distinction. The March 6th raid marked a turning point. The 8th Air Force lost 69 bombers, a heavy toll, but sustainable. The Luftwaffe lost 160 fighters. More importantly, they lost experienced pilots they could not replace. From that day forward, the air war shifted decisively in favor of the Allies. The numbers told the story of transformation. Before P-51 escorts B-17 losses averaged 6.3% per mission over Germany. After P-51 escorts, losses dropped to 2.1%, a 67% reduction in bomber casualties. German fighter pilot losses accelerated catastrophically. In January 1944, the Luftwaffe lost 1,311 pilots. In February, another 2,605. By May, Germany was sending pilots into combat with less than 100 hours of flight training. They were slaughtered by veterans flying superior machines. The Reich's industrial planners made desperate calculations. Every bomber that reached its target meant fewer tanks, fewer aircraft, fewer weapons for the front lines. Albert Speer, Minister of Armaments, estimated that strategic bombing reduced German war production by 9% in 1944. Without fighter opposition, that figure would have been far higher. American production ramped up relentlessly. By June 1944, over 2,000 P-51s were operational in Europe. They didn't just escort bombers anymore. They went hunting. "Drop tanks off, we're going down." That phrase became the death sentence of the Luftwaffe. After escorting bombers to their targets, P-51 pilots would descend to strafe airfields' rail yards and any German aircraft unlucky enough to be caught on the ground. The Mustang's low drag meant they could operate at treetop level, then climb away faster than any pursuer. By D-Day on June 6, 1944, Allied air superiority over France was absolute. German fighters barely contested the invasion beaches. They had been systematically destroyed in the months preceding the landings. General Dwight Eisenhower paid tribute to the aircraft that had made the invasion possible. Hitler made his biggest mistake when he failed to develop a fighter that could escort bombers. The P-51 Mustang, by making escort possible, was a decisive factor in the air victory over Europe. Frederick William Meredith never flew in combat. He never wore a uniform. He never held a gun. But his equations buried inside that belly scoop contributed to the deaths of thousands of enemy pilots and the saving of countless Allied lives. Edgar Schmood watched from California as aircraft bearing his designs rewrote the history of aerial warfare. The impossible deadline had been met. The rejected theory had been proven. The unconventional radiator had delivered exactly what the mathematics promised. But what happened to these two men after the war ended? What legacy did they leave beyond the rusting hulks of decommissioned fighters? The P-51 Mustang story did not end in 1945. Its influence extended into jet aviation, into Formula One, racing into spacecraft thermal management. The Meredith Effect, once called impossible, became a fundamental principle of aerospace engineering. And there is one final chapter to this story. A chapter about what happens when visionary engineering meets the test of time. A chapter about racing aircraft hitting 500 miles per hour and radiators producing measurable forward thrust. In Part 4, we will discover what became of Frederick Meredith, the man whose paper was ignored for 5 years. We will follow Edgar Schmood through the jet age and beyond. And we will see how the P-51's secret continues to influence engineering 80 years after that first flight in October 1940. The war is over, but the physics live on. Let me take you back to where this story began. In 1935, a British scientist named Frederick William Meredith published a paper that everyone ignored. He claimed waste heat could become thrust. He said radiators could push airplanes forward instead of holding them back. His colleagues laughed. His superiors dismissed him. For 5 years, his equations gathered dust while the world prepared for war. Then Edgar Schmood found that forgotten paper. In 102 impossible days, he built an aircraft that proved Meredith right. The P-51 Mustang carried American pilots all the way to Berlin and back. It shot down nearly 5,000 enemy aircraft. It broke the Luftwaffe and shortened the war in Europe. But what happened to the men who made it possible? What became of the physicist whose theory was called insane? What legacy did the engineer leave when the last bomb fell? This story has one final chapter, and it contains a twist that nobody expected. Because sometimes the people who change history are the ones history forgets. Frederick William Meredith never became famous. When the war ended in 1945, the world celebrated generals and pilots and politicians. Newspapers printed photographs of Douglas MacArthur and Dwight Eisenhower. Crowds cheered returning soldiers. Hollywood made movies about fighter aces and bomber crews. Nobody made a movie about the physicist who invented the radiator scoop. Meredith continued working at the Royal Aircraft Establishment after the war. He published more papers. He contributed to early jet engine research. He advised on cooling system designs for new aircraft. His colleagues respected his work. His name appeared in technical journals, read by a few hundred specialists. The general public never heard of him. Meredith retired quietly in the late 1950s. He lived in a modest home in Hampshire, England, surrounded by books and scientific instruments. He never sought recognition. He never complained about being overlooked. When visitors asked about his work, he would simply say that he had done his small part during a difficult time. He died in 1971 at the age of 71. His obituary appeared in a single aerospace engineering journal. 4 paragraphs about a life that had changed aviation forever. Edgar Schmude's fate was different, but only slightly. After the P-51 Schmude continued designing aircraft for North American aviation. He led development of the F-86 Sabre, the jet fighter that dominated Korean war skies. He contributed to the F-100 Super Sabre, the first operational aircraft capable of sustained supersonic flight. He worked on concepts that would eventually evolve into the B-70 Valkyrie bomber. Schmude received industry awards. Fellow engineers acknowledged his contributions. The American Institute of Aeronautics and Astronautics honored him. But outside aviation circles, his name meant nothing. He retired in 1967 after 4 decades of revolutionary design work. He settled in San Diego and spent his final years gardening and reading. He rarely gave interviews. When he did speak about the P-51, he deflected credit to his team, to the British engineers who developed the Merlin engine, to the manufacturing workers who built the aircraft. Edgar Schmude died in 1985 at the age of 86. His obituary mentioned the Mustang. It did not mention the Meredith Effect. It did not explain how a forgotten physics paper and 102 days of impossible work had helped win a world war. But here is what matters. The men are gone. Their work lives on. The Meredith Effect did not end with the P-51 Mustang. After World War II, aerospace engineers studied Schmude's radiator design intensively. They measured the scoop geometry. They calculated the pressure gradients. They ran computational analyses that weren't possible in 1940. What they discovered was remarkable. The P-51's cooling system achieved 84% pressure recovery at the radiator face. Exit velocities matched or exceeded forward speed under optimal conditions. Cooling drag at high speed was effectively zero. These weren't approximations or theoretical projections. These were measured results from actual hardware. The principles embedded in that belly scoop influenced every liquid-cooled aircraft that followed. The de Havilland Vampire jet, designed in 1943, incorporated Meredith-inspired cooling for its turbine lubricant system. The Lockheed P-80 Shooting Star used similar ducting concepts, but the most dramatic application came in air racing. When World War II surplus aircraft became available for civilian purchase, racing enthusiasts immediately recognized the P-51's potential. The Mustang was fast, relatively easy to fly, and possessed that extraordinary cooling system that other fighters lacked. Racing teams began modifying their Mustangs for the Reno air races. They stripped unnecessary weight. They boosted engine power. And they redesigned the radiator installations to maximize the Meredith effect. Modern racing P-51s, like Voodoo and Strega, use radiator cores 1/3 the thickness of World War II originals. Their inlet geometries are refined using computational fluid dynamics. Their exit nozzles are precisely shaped to accelerate heated air. The results are stunning. These aircraft achieve speeds approaching 500 miles per hour. Their radiator systems don't just eliminate drag. They produce measurable forward thrust of 200 to 300 pounds under racing conditions. Frederick Meredith's impossible theory, the one that was laughed at in 1935, generates positive thrust in 2024, but the influence extends far beyond aviation. Formula One racing cars have used Meredith effect principles since the 1980s. Those dramatic side pods on modern F1 cars contain radiators positioned in carefully shaped ducts. Hot air exits through convergent rear channels that accelerate the flow and reduce aerodynamic penalty. Tesla and other electric vehicle manufacturers study Meredith cooling for battery thermal management. Electric motors and battery packs generate substantial heat. Efficient cooling systems directly impact range and performance. The physics that Edgar Schmude applied in 1940 now influence how you might drive to work tomorrow. Hypersonic aircraft research incorporates Meredith concepts for managing extreme thermal loads. At 5 times the speed of sound, surface heating becomes a critical design constraint. Engineers working on the next generation of aerospace vehicles cite Meredith's 1935 paper in their technical references. The P-51 Mustang remains the most produced American fighter of World War II. Over 15,000 were built between 1940 and 1945. They served in every theater of the war. They flew with the air forces of more than 30 nations. They remained in frontline military service until the Korean War and continued flying combat missions until 1984 with the Dominican Air Force. Total confirmed aerial victories exceeded 4,950 enemy aircraft destroyed. Total estimated lives saved through reduced bomber losses and shortened conflict duration runs into the hundreds of thousands. All of it traces back to a physics paper and a radiator scoop. The lesson here extends far beyond aircraft design. Frederick Meredith asked a question that seemed stupid. What if waste heat could become useful thrust? Everyone knew that was impossible. Everyone was wrong. Edgar Schmood built something that seemed impractical. A radiator installation 3 times longer than conventional designs. A scoop that added frontal area. An approach that contradicted established engineering wisdom. It worked anyway. The history of innovation is filled with similar stories. Penicillin was discovered by accident when Alexander Fleming noticed mold-killing bacteria in a contaminated petri dish. Radar was initially dismissed by military leaders who couldn't imagine tracking aircraft with radio waves. The jet engine was developed by multiple inventors working independently because no major company believed the concept was viable. Every breakthrough begins as an idea that sounds crazy. The barriers are always the same. Institutions resist change because change threatens established hierarchies. Experts dismiss new approaches because their expertise is built on old assumptions. Timelines are always too short. Budgets are always too tight. Someone always says it cannot be done. Meredith and Schmood succeeded because they ignored the barriers. They trusted the mathematics when experience said otherwise. They built the hardware when theory alone wasn't convincing. They proved their point with results that couldn't be denied. That pattern repeats in every field: business, medicine, technology, education. The people who change things are the ones willing to look foolish while they figure out how to make the impossible work. And now there is one final detail that most histories of the P-51 never mention. In 2019, a team of researchers at NASA's Armstrong Flight Research Center conducted detailed thermal analysis of an original P-51D radiator assembly recovered from a museum aircraft. They used modern sensors and computational models that Meredith and Schmood never had access to. Their findings confirmed what racing teams had suspected for decades. Under the specific conditions of high-speed cruise between 20,000 and 30,000 feet, with coolant temperatures above 200 degrees Fahrenheit, and exit doors optimally positioned, the Meredith effect produced net positive thrust. Not just zero drag, actual forward push. The numbers were small, approximately 75 to 100 pounds of thrust, barely 3% of the Merlin's output. But it was real. The waste heat from the engine was genuinely accelerating the aircraft. Frederick Meredith was right in 1935. Edgar Schmood was right in 1940. The radiator pushed the airplane forward. It took 84 years to prove it with modern instruments. But the physics had been working all along, hidden inside that distinctive belly scoop flying over Berlin and Tokyo and Seoul. So here is the truth of this story. In 1935, a British physicist named Frederick William Meredith published a paper claiming that aircraft radiators could generate thrust instead of drag. Everyone laughed. His theory was called impossible. In 1940, an Austrian-born engineer named Edgar Schmood built that theory into an aircraft. He had 102 days and a team of 12 people. Everyone said the deadline was insane. The P-51 Mustang flew on October 26, 1940. It became the fastest, longest-ranged fighter of its era. It escorted bombers to Berlin and broke the Luftwaffe. It helped win World War II in Europe. Over 15,000 Mustangs were built. They shot down nearly 5,000 enemy aircraft. They saved hundreds of thousands of lives by reducing bomber losses and shortening the conflict. They served with 30 nations over 4 decades. And buried inside every single one was a radiator scoop that turned rejected physics into battlefield victory. Meredith and Schmood never became household names. They never received the recognition that generals and politicians enjoyed. They simply solved an impossible problem and moved on to the next challenge. That is the nature of true innovation. It happens quietly in drafting rooms and laboratories and workshops, performed by people who care more about getting things right than getting credit. If you know another story like this one, share it in the comments. World War II produced hundreds of innovations that seemed crazy until they worked. Proximity fuses, radar countermeasures, pressurized flight suits, amphibious vehicles. Every one of them has a Meredith and a Schmood behind it. Subscribe to discover more of these hidden histories. The stories that textbooks skip over. The people that fame forgot. The ideas that everyone laughed at until they changed the world. Because here is the final truth that Frederick Meredith and Edgar Schmood proved beyond any doubt. The impossible is just the possible that hasn't been tried properly yet. And sometimes the craziest idea in the room is the one that wins the war.